harder version than someone else? No. All right. So yeah, now the stream's up. So yeah, test next week. If you all came in, I've got note cards here, the 5x8 note cards. Remember, you can put anything you want on this note card and bring it in. You can type things up and print them and glue it to the 5x8 note card. Front and back is cool by me. The only thing you are not allowed to do is staple a bunch of loose papers to it. No flip books. I mean, sounds obvious, but good for me to clarify that. Now, what's cool, so this test, you get a 5x8 note card. The next test, you get a separate 5x8 note card. You don't have to use the same one. And then the final, you get 2 5x8 note cards. Because you can just take the ones from the first 2 tests. Now, I say that with the caveat that on the test, on the final, there's a little bit extra we'll cover. So the first 2 note cards will get you most of the way. But something to keep in mind when you're making this one, the last test, if you want to leave a little bit of space. That's up to you. It doesn't really matter to me. All right, so, and I say that, for the final, you'll either get to use 2 5x8 note cards or just 1 full sheet of paper front and back. If you just take 2 5x8 note cards, it makes a whole sheet of paper. It works out real nice that way. Anyway, there you go. This week, we actually don't have a ton to cover, so we're probably going to get close to, if not finish, most of it today. Maybe a little bit will roll over into Thursday, and so that's going to let us start reviewing sooner, which is nice. But as far as what to start thinking about now, what should I start studying? What should I start looking at? How should I make certain I'm ready? Sound like a broken record. The problem sets and the quizzes and the clicker questions are your 3 main sources to look at. The problem sets have the math in them. The clicker questions are conceptual questions. And then the quizzes, is kind of representation of what the test is going to be like, because it's a combination of conceptual and problem set and numerical problem solving. So that's what I would like for y'all to be looking at. How do you make certain you're ready for it? Solve problem, look over your old problems and look at a problem and say, do I know how to go about this? If your answer is yes, you can probably skip that one and move on to one you don't know how to do. That's kind of your way of going through it and looking through it. If you're unsure, just solve it. Now, reminder to you all, when you're solving a problem, do not have the worked out solution literally there as you're solving through it. Because again, it's one of those things where you're not going to have the worked out solution when it comes test time. You should study in a way that matches the test. Now, to that end, it's fine to have the answer there, because the answer doesn't really tell you that much, to be honest. When you have the answer there, it doesn't show you how to solve the problem. But definitely don't have the worked out solution just right there. You can refer to it if you get stumped. In fact, I encourage you to. But do not just go through a worked out solution and say, yep, that makes sense. Because that will give you a false sense of security. It's it's a classic. When I solve a problem, it may make a lot of sense, but then when you try to solve a problem, you're like, wait, what? It's that same kind of feeling. So, anyway, make sure you're doing that. Go through the old quiz. I just posted the solution to the last quiz. So every Tuesday I do that. Next week, Tuesday, I'll post the solution for this week's quiz. Now, the only little bit of kind of challenge we run into. So the good news is today we're going to get through most of the stuff that you need for the last chunk. The quiz for the stuff we're covering this week, like every other quiz, will not be due until Saturday. That is after the test. I do not recommend waiting until after the test to take the quiz. The reason for that is it's better that you take the quiz, see what parts you understand and don't understand, learn from that, and then do great on the test, as opposed to taking the test, realizing you don't understand those parts, and doing better on the quiz, which is worth less points. So, use the quiz as your study tool. Don't use the test as a study tool for the quiz. Use the quiz as a study tool for the test. So, this stuff on the quiz that is due next Saturday, that's going to be on there. We're going to finish it this week, which is before the test, which is next Thursday. In case anyone wasn't clear, the 15th is our first test, just to make sure everyone's on board with that. So keep that in mind, you all. towards that end, you should at least do the first attempt of your quiz sometime before the test. That's kind of the punchline. Whether or not you wait for the second attempt, that's fine. But at least do the first attempt so you can make certain you get some feedback and make certain you're as ready as possible. So, I think remember 22 multiple choice, pick 2 free responses. 2 free responses, pick 1 out of those 2. I'm optimistic on this go. You do not need to bring a Scantron. I will hand you the only thing you need is a calculator, a pencil, and ideally your 5x8 note card. You do not need anything else. Also, I guess your UCF ID, because at the end, I literally will just check that your UCF ID's name matches the name that you wrote on the thing. I will give you, part of your all's test, the last page will be the Scantron. It's printed on a piece of paper. I can scan it with my phone. I like it better than the UCF ones because I get immediate feedback in terms of how you are doing. So the last page will be your Scantron. You'll see that when we get there. I'll mention that. But when we get to the test, just, I have it in all bold caps. Make sure you write your name and bubble in the PID, all that jazz. We'll talk about that. I will get here early on the day of the test. I'll get here 10 minutes early. I'll give the spiel 5 minutes before things begin, because the second that it hits 4:30, I'm going to start passing out tests. Because I want to give you all as much time as possible. In fact, I may start handing out tests 2 minutes before then even. And it's a small room. I'm another proctor. It won't take me long to get them to all y'all. It'll be quick. Make sure you all have the max amount of time as possible. Last thing I'll mention, if you make use of accommodations, either you are using them or you're on the fence of using them, please do take advantage of them. If you have that extra test time accommodation, please reach out to SAS and schedule the test. So then I send it to them. You'll take it there. It's great. Please, if you have accommodations, use them. I want you to. I want everyone to have equal opportunity, and that is an equity thing. And I want you to have what you need to be successful. At the end of the day, my hope is that none of you feel constrained for time. And that's one way to kind of make it equitable. I've done my best to make it so that you have enough time to process the information and then also go back and double check your work. So we'll see how that all pans out, but that's the hope with the test design. It's enough questions so that it doesn't kill you if you miss one, but not so many questions that you don't have time to check your work and think through it and all that kind of jazz. It's a delicate balance I have to reach. Okay, so what's going to be on the test? Everything in problem set 1. So if you go to problem set 1 and you're kind of, everything in problem set 1 is kind of free game. So when you open problem set 1, you should be able to kind of go through that and say, yep, I know how to solve that problem. I know how to solve that problem. And again, we'll kind of talk about this more next week. Make certain you're good with vectors and electric fields. So, if we just kind of go to the top here, it's got all 5 sections. Charges and electric forces. So make certain you can find the force due to a few charges. Electric fields and Gauss's law. Make certain you can find the electric fields due to a point charge, several point charge, line of charge, sphere of charge, plane of charge. Remember that the plane of charge is the fancy one that doesn't depend upon distance. It's got that weird thing to it. That's an important thing to remember. Electric potential, electric potential energy, voltage, and electric potential energy. Not the same thing. Don't get them twisted. That's one of those things I mentioned a few times. We talked about capacitors and resistors a little bit last week, and then this week we'll kind of finish up with current resistance. But yeah, this is everything you need to know. If you've been feeling good up to this point, if you've been doing well in the quizzes, if you've been doing well in the problem sets, this should go great for you. Honestly, if the test doesn't go well and everything else has been going well to that point, please come and talk to me after the test and we'll kind of talk about, because I want to know what's going on there, because that means I am not giving you the resources you need to be successful and there's some disconnect. Because the Scantron is easy for me to grade, I will have the grades for the Scantron in, probably by the next day. So the Scantron grades, which is 80% of the test, I'll have those scanned and in next day probably. If not the next day, then by Monday. The free response portion of it, I've asked the TA to have that graded within 2 weeks' time. Gives them time to actually grade it carefully. I would rather them spend longer grading it and doing a good job of grading it than grading it quickly and not giving you all the points you deserve, because remember there's a partial credit rubric. So I've given them 2 weeks. It may be quicker. It should not be longer. So we should have that extra 20%, whatever that is, by the end of February. My biggest goal is that by the end of February, you know how you're doing in the course. So one of the things right now is your grade in the system doesn't quite match your actual grade due to a variety of things. So for example, remember your all's quizzes? They're not graded out of 5 points. They're graded out of 4.5 points. I have to manually transfer all your quiz grades from those 5-point ones to kind of ones that I've made that are worth 4.5 points. There's no way for me to automatically do that, so I'm not constantly doing that. I do that one big bulk thing after the test. I will transfer them over so you can actually see how those affect your grade. The clicker questions, remember, are not graded. Say I've asked 20 questions. I will not grade it out of 20 points. I will grade it out of 15 points, 75% of that. So I have to do that as well. There's a lot of manual things I have to do that unfortunately web courses can't do automatically. So to that end, after the first test, within a week after that or so, your grade in web courses will actually be accurate to what your grade is in the class. Whereas currently it is not. And then that'll give you some feedback. That'll let you know if you need to make changes. That'll let you know if you're concerned about withdrawal, stuff like that. The withdrawal is not for I forget what the deadline is. It's a long ways after that. But you'll know well in advance if that is a concern for you. I hope it's not for many. Last year, I had very few people withdraw. But if that's you, that's okay. Withdrawing doesn't mean you failed. Withdrawing just means, all right, next time I got to make some changes and then I'll do great. That's why it's an option. So anyhow, learn from mistakes, all that kind of jazz. But yeah, that's kind of the information grade-wise, logistics-wise, as far as how things are going up to this point. Your grade right now does not match your actual grade in here, but it will after the first test. And then after the second test, I'll do the same thing and all that jazz. Any questions about anything? All right. If you're concerned, confused, any of those things, shoot me an email, y'all. If you're stressed about this test coming up and you don't know what to do, shoot me an email. I want to make certain you all go into this as confident as possible. This test is not just testing you, it is also testing me. Which sounds silly, but it's literally, when I look at your all's grade as a collective, that's an indication of how I have done as a teacher. So, it's also a test of how I've done preparing you all as a collective. If everyone fails, I'm the only common denominator. So I messed up, I'd figure that out, hear from you all that kind of jazz. But yeah, I don't think that'll happen. I'm not expecting that to happen, that's for sure. But yeah, there you go. All right, so let's go ahead. Last class we finished up. Just to give you a recap what we did last week, we talked about capacitors. So capacitors are these things that they're two parallel plates. They are literally defined capacitance, how much charge per voltage. So they're basically like buckets, but for charge. Now this charge, we get big old plates that they can spread out on, 2 of them. One gets positive, one gets negative. And we pump a bunch of charge on them, and they build up. Now capacitance is defined a few ways. One of those was epsilon naught A over D. That's somewhere in here. There it is. All right, so one, we have epsilon naught A over D. We also have Q over V. Q over V is I don't want to use the word made up, but that's like the base definition of how much charge can I put per volt applied. This volt is what's actually pushing the charge on there. There's potential difference, and we're going to talk about that today. You need a voltage to pile up charge in there. The more voltage, the more charge. So if we want to give it like a standard, how much charge can they hold? We do charge per voltage. That's how they store charge. That's purely based on geometric quantity. Literally, how big is the plates? How far apart are they? Epsilon naught A over D. Epsilon naught is 8.854 to minus 12. All right. And then we introduced the dielectrics, and we said these things increase how much charge, but the math was really simple. You literally just chuck where is it on one of these? You literally just put kappa in front, the dielectric constant in front of it. So instead of it being C equals epsilon naught A over D, now it's C equals kappa epsilon naught A over D. If it has a dielectric constant of 5, it can hold 5 times the charge. If it has a dielectric constant of 10 times the charge. And then we did some problems with that. We talked about resistance. Resistance is the thing that resists the flow of electricity. And we had this idea of resistivity. Materials, different materials are better conductors. The lower the resistivity, the better they are at conducting electricity. And you can see examples here. Wood, really high resistivity. It's not a good conductor. Copper, low resistivity, conducts it well. Why do different materials have different resistivities? Super complicated question, but the easiest answer is if they're a conductor, the electrons are free to wiggle around. Insulators, they're trapped. They're stuck to the atoms. And we'll talk about today why that is. We also said as temperature goes up, things get hard, like the molecules literally wiggle around, and those moving charges, it's literally harder for them to get through because they get knocked around by these atoms that are wiggling all around. It's kind of a simplistic definition. Bam, bam, bam. All right, and then we introduced resistance. We're going to talk more about that today. But the one I wanted to focus on last class, resistance, like capacitance, is based on what it's made of and the shape of it. So capacitance was based on the dielectric and based on area and distance between plates, what it's made of, and the geometric quantities. Resistance is the same way. We're going to be working with that a lot more today, doing some problems with that. This top part here, we'll get to that. But for now, we just cared about this resistivity. R equals rho L over A. Longer the wire, more resistance. Bigger the area, less resistance. And then we did a problem with it. And this is the one that we didn't like. It was we had to go through some steps. But I said, what happens if I change the diameter? If I make the diameter smaller. So if we make the diameter smaller of this wire, it's like taking a 4-lane road and make it into a 2-lane road. And basically that immediately should tell us that we're going to have more resistance. It is harder to fit a bunch of cars in a 2-lane road than a 4-lane road. Now that kind of narrowed down to 3 options. And so then the question been, how much more resistance do I have? We had to recognize that this wire was a circle. So it's a circular cross section. Circles have an area of pi r squared. Then you had to realize that radius is diameter divided by 2. And we plugged all that stuff in. This is a good one to look back on. This is kind of the worst case. So I love problems like this where I say, hey, I changed this variable. How does it affect another variable? I double this. How does it affect this? I triple this. How does it affect this? This is kind of the worst case scenario of that. Because you had to do a couple steps there. You had to recognize area was pi r squared, and then you had to recognize that radius was diameter over 2. So this is a great one to look at, think through, process through. It's as bad as it gets. And then this one was the same thing. I said I half the radius and move from there. All right. So what I want to do real quick is solve this problem. What is the radius of a copper wire with a resistance of 50 ohms and a length of 0.5 kilometers? And there I give the resistivity of copper. That is a necessity. I do not expect you to have resistivities memorized. The only givens that you all need to know will be on your formula sheet. Let me rephrase that. The only constants you all need to know are given on the formula sheet. So mass of an electron on the formula sheet. Mass of a proton on the formula sheet. If there is a constant like this resistivity of copper, I will give that to you in the problem. You do not need to look up a bunch of bajillion constants and write them on your 5x8 note card and try to guess which ones I'm going to ask. No. If you need a constant, I'll give it to you. All right. So, step 1, what's given? We are given resistance, 50 ohms. Ohms. Okay, so this is something I didn't necessarily talk about before. This is the Greek letter omega, capital Greek letter omega. Omega sounds like, if we just shorten it to ohms, that's where it comes from. That's why we chose it as our symbol. The guy who came up with resistance, I forget, his name had to do with ohms. And I think maybe his name was ohms. I forget exactly. It was related to ohms. So we chose this capital Greek letter omega for the symbol. R is the symbol. So R stands for resistance. Ohm stands for the unit. And we'll see that more today. Okay, in fact, I'll just write that. Ohms, O-H-M-S is how you spell that word, in case you're like, how do I spell that out? All right, so we got that. We also have a length of 0.5 kilometers. So length equals 0.5 kilometers. We do have to convert that. So that's going to be 0.5 E3. If you're going from kilometers to meters, you just multiply it by 10 to the 3. Unit conversions, great thing to put on your note card. Okay, and we got the resistivity of copper. Remember, this resistivity is based on the material, and it's how easy or hard it is for electrons to flow through it. Copper. very easy for it to flow through. So it's got a very small number. All right, and we are solving for radius of the copper wire. All right, give you all like 20 seconds, 30 seconds. See if you can think of what equation we're going to use to solve this. Because that's always, in my opinion, the hard step. Write down your givens, write down your missing. If you can find the equation, if you can do steps 1, 2, 3, the hard work's done. What equation is going to relate to resistance, length, resistivity, radius? And who knows, maybe it won't use everything. They generally do. But it's possible I give you more information than you need in a problem. Now the good news at this point, there's only 2 equations that actually have resistance in it that I've kind of emphasized with you. In fact, one of them I haven't really even talked about. So the 2 options really, we're going to learn that V equals IR. We're going to talk about that today. It showed up in the slides, but if we look at that equation, great, it's got resistance in it. We don't know voltage. We don't know current. Probably not a good choice. So, nope, not that one. The other one was resistance equals rho L over A. You look at this one, you say, this has a lot of the things that were given. It's got resistance, it's got length, it's got resistivity, but I don't see a radius in it. And this is where you have to go that extra little step and remember all wires are circular. No one's going to find a square wire. They just don't make them. They're always circular wires. So the area here is pi r squared. It's the area of this wire, the cross-sectional area of this wire. How wide, kind of like how much room is there for those electrons to move through. So we replace that A with pi r squared and we say, okay, I can work with this. Now again, at this point, you can do the algebra with the variables, or you can just start putting in numbers and do the algebra. I'll do the latter. So 50 equals 1.72 e to the minus 8 times my length, which is 0.5 E3, divided by pi r squared. We will simplify everything we can simplify, which in this case means the right side. We're going to take, before you do algebra, simplify what you can. There is no reason to, I do not want to divide by 1.72 and then multiply by pi and then divide by 0.5. Let's just simplify before we do the algebra. Algebra is usually the hard step. So if we can reduce how many times we have to move things around, the better. So if I simplify that right side, I do 1.72 e minus 8 times 0.5 E3 divided by pi, and then I check my calculator to make certain I actually plugged everything in correctly. Always a good step to do. We get 50 equals 2.737, 1, 2, 3, 4, 5, 6 to the minus 6, all divided by r squared. And this is the algebra that's been given a lot of my high schoolers challenges. May give you all challenges as well. Whenever the variable you want is on the bottom, you need to multiply it over first. So you're just going to multiply that r squared over, so I get 50 r squared equals 2.737 e to the minus 6. And then we're going to divide by 50 to get rid of that, and then square root it to get rid of that squared. And that's kind of the 2 next algebra steps. So square root of my answer, 2.737 e to the minus 6. Whenever you do square root, make certain you parentheses and that everything you want is in the parentheses. And we get an answer that doesn't fit on my paper, so I'm going to move things over a little bit more. And we get that r equals 2.34 e to the minus 4 meters. Okay. And we'll look at our answer and see if it makes sense. This is 0.2 of a millimeter. It is very tiny. This is a very thin wire. But what's kind of cool about this problem is it just shows you, so 50 ohms, that's a low resistance, but it shows you how good copper is. You make a wire that's half a kilometer long, and it's this thin. This is like a super thin wire, it's hard to do with my fingers how thin this thing is, and it only has a resistance of 50 ohms. So copper, fantastic conductor. In fact, in most of the problems that we solve as time goes on, we're basically, anytime there's a copper wire in our circuit, we'll basically pretend it's not doing anything. We're pretending that it doesn't even contribute to the resistance because it has such a low resistivity to it. So you'll see what I mean. This will be stuff we do after the test. I don't know if this is sad news or good news. Sadly, on the 22nd, there's going to be a guest. I'll have a substitute teacher, basically. My high school classes, we have a Busch Gardens field trip that day. So sorry, y'all. To be fair, I won't be at Busch Gardens while you all are in class. I'll be on the bus on the way back home. But we're not getting back till 7, otherwise I'd be here. So we are going to have someone one of the other professors who come in, Dr. Vida. He's great. So he's going to cover the class for me that day. I will also post a live stream from when I taught the exact same class last year. So you'll have kind of 2 options. But I'll give you all a heads up that way, just so I don't forget. Class will still exist. We'll still be covering stuff. I won't recover it next time. I may give a recap. But just wanted to let you all know sooner than later. That's after the test, though, so future problems. All right, fantastic. All right, this one, don't even bother with it. This is in the problem set. I have talked about this whole temperature increasing things. All I need you to know is as temperature goes up, resistance goes up. That's what I need you to know. I do not need you to be able to do the math with this. If this is a calculus-based course, I would spend the time and energy on it, but for you all, not worried about it. I would need to cover this and actually do the math for engineering students because if they're building circuits, this is something you have to take into account. Things get hot. Your computer gets real hot. 70, 80 degrees Celsius is kind of what your computer's generally running at inside of it, which is only 20 to 30 degrees Celsius off the boiling point of water. It's hot. You touch it, it ain't going to feel too great in the CPU and stuff like that. So you have to care about this as far as when you build circuits. But for you all, I'm going to not worry about it because it's not critical to you all. But you do need to know as temperature goes up, resistance goes up. As temperature goes down, resistance goes down. All right. So there you go. Fantastic. We got through that. So moving on to kind of this week's stuff, which is kind of overlapped. We're going to be mainly focusing on the flow of electrons in a circuit. That's going to be called current. And we're going to be talking about what happens when you put these resistors in an actual circuit. So up to this last week, we talked about capacitors. These are things that can hold charge. We talked about resistors. These are things that can resist the flow of electricity. And we kind of just talked about them as far as what they do. Now we're actually going to start to put them into circuits. We'll get into it a little bit. Most of circuits will actually be after test 1, and we'll really get into the weeds with circuits. It's one of my favorite topics just because we're going to talk about how electricity works, y'all. That magic juice that flows to the walls that all of us makes use of and no one knows how it works. I mean, most people, they know if you plug something in, and don't put your finger in the socket. That's usually what most people know. But as far as what the heck it is, how it works, how we even make it, all that stuff, even though it's so critical to society, most people have no clue what it is, how it works. And this will actually be some useful stuff for you all. If you ever end up owning a house, there'll be some things that come into play and whatever. It'd be great. All right, not too worried about this one. We actually think we already solved that one. Still not worried about that, and bam, bam, bam. So we're just going to skip through those. Okay, so here's some things we need to remember before we get into current and resistance. You need to remember that electrons are the things moving, not protons. And why is that? You have to remember where is a proton found in the nucleus. So literally, if protons were the things moving around, If you have a single proton flying around, that is literally a hydrogen atom. A hydrogen atom is defined as one proton. So, if in a wire you say it's the protons flowing, that means you're saying in a wire hydrogen atoms are flying through the wire, which is not the reality. I don't know if you like that or don't like that, but that's how it goes. Electrons, they're totally free to fly. They're 1,000 times smaller than a proton, so they're much smaller, but they're also not stuck inside a nucleus. And the conductors, they are free flowing. You got the sea of electrons, and they can kind of go where you want them to. They are free to move and groove. You got to remember about voltage. Voltage is not energy. Voltage is not energy. Voltage is the potential. That's another name for it, was potential. Electrical potential. And you need a difference in potential. That's one. Things will go from, electrons will go from low voltage to high voltage. Really important concept. Protons will go from high voltage to low voltage. And then getting to our next point, all charges go to lower energy. Okay, so again, really hammering that concept. Voltage, electric potential, energy, not the same thing. Voltage is kind of like height. Energy is like potential energy. I don't know. There's not. So there's that, and yeah, there's a relationship between them. The energy equals the voltage times the charge, whatever that charge may be. And yeah, there you go. Charges move from higher to lower energy. And you know what? I'll even clarify here. Electrons move from low voltage to high voltage. Protons move from high voltage to low voltage. And we did some clicker questions. Great clicker questions for y'all to go back and look at that we kind of talked about that. But yeah, that's some previous concepts we're going to need to understand why and how electricity flows through a wire. Okay. So what we're going to talk about today is we're going to talk about what current is and how batteries generate current. That latter part, how batteries generate current, that's going to be like super brief. Like I'm not going to get too much into the chemistry of it, but I'll briefly talk about it. We're going to talk about what resistance is. We kind of already have, so that's kind of covered. We're going to talk about the relationship between current, voltage, and resistance, i.e. Ohm's law. Super easy equation. It's going to come up later, but you know, it's always good. There it is, V equals IR. We're going to see that later. It's such an easy relationship. So simple. Like it's as easy as a math problem as I can give you. I guess addition may be easier. I don't know. V is voltage, I is current, R is resistance. We will see those, but hey, the more you see it, the better you remember it. And then we're going to talk about power, which if you all remember from your Physics 1 class, power was a word that you hopefully have heard at some point. Power is defined as the energy used per second. The energy used per second. So we'll talk about that. We'll actually learn how to calculate your electric bill. How exciting. Which sounds silly, but you know, it's good to know what you're getting charged for. And where that calculation comes from. And when you're choosing your next light bulb and you see a bunch of things that say watts on them, actually knowing, fun fact, watts is power. A little foreshadowing. So you'll learn why light bulbs say they're 50 watts, 60 watts, whatever they may be. Again, so much actual practical knowledge. I love circuits. It's great. All right, so here's current. Current is defined as, and again, this is a little bit in calculus terminology, so I'm going to go ahead and put it in a more general sense. Current is defined as how much charge is moving per second. So if we kind of make that more general, instead of D, we're going to put a delta. So the change in current, or the change in charge divided by the change in time. How much charge is moving through something every second? It's like a flow of water. I mean, literally think of the word current. The first thing that comes to your mind is probably water. How fast is the water moving? Electrical current, kind of the same idea. But it's not just how fast it's moving, it's basically how much is moving through it. For example, I can have a big old wire. They don't have to be moving fast for me to have a lot of current moving. Because it's a big old wire. There's more of it that can be moving. If you think about an ocean or like a river, if I had a really wide river, even if it's moving slowly, that's a lot of water moving if it's really wide. So this current is not necessarily how fast they're going. That's one piece of it. But more specifically, it's how much charge is going through something every second. The rate of flow. Now, here's the bummer with this. It's defined as the rate, I was checking up my next question, I didn't want to give away too much. The rate of flow of positive charges, which is a bummer, because I already told you all that positive charges aren't flowing. Now, why is this? Because historically, that's what they decided, and then at some later point, they learned that positive charges aren't moving, but at some point, it's too late. They've already decided. So it is the rate of flow of positive charges, even though that's not what's actually happening. So again, that's why that's an important kind of concept. Positive charges are not flowing through the wire, but mathematically, a flow of positive charges is the exact same as a bunch of negative charges going the other direction. So mathematically, it actually works out perfectly fine, no problem. So even though this is defined as positive charges moving, so if current's to the right, in fact, yeah, so here, these are all positive. This is not what's actually happening. In fact, let's make these all negative. If I said, what's the direction of current here? It's actually the other way. Big bummer, but it is what it is. I don't make the rules, I just teach them. But it's one of those, too far gone, we can't change it, it's set. Like, too many things have been, even if something's not precise, as long as it works, at some point it gets set in stone. The unit for this is ampere, short amps. So if I want to say how much current, I would say 3A, which stands for amps. So that would just be 3A. 1 amp is a lot of current. To give you all a sense of reference when you're solving problems, what's reasonable, that kind of thing. 1 amp is a lot of current. That's your all sense of reference. 1 is a lot. So generally current will not be up to 1 amp. If you have that much current running through something, it will generally get pretty warm. Because if you actually think about, so remember I said as temperature goes up, resistance goes up? Well, fun fact, as charges are moving, they heat up the wire. So it kind of gets this whole cycle started where it gets hotter and hotter and hotter. That's how your all's fuses work. They get so hot. Fuses are literally designed so when if you have a 3 amp fuse at your house, which you do, somewhere in your thing, for example, your air conditioner has a fuse in it. That fuse is literally a tiny little thin piece of metal, and when that amperage is met, when that amount of current is met, let's just say it's a 5 amp fuse. When it reaches 5 amps, it gets so hot it melts the wire and it breaks the circuit and the electricity stops flowing. You may be like, why would I want my thing to break? It's better that your fuse breaks than the really expensive things that come after it. A fuse costs a few cents. Go to like Home Depot and you can get them for like 20 cents, 50 cents. Versus your air conditioning unit where 7 amps goes through it, so 5 amps is kind of our limit. If 7 amps goes through it, you have things after that that are going to break that cost way more money. And if you're really unlucky, you'll get a huge power surge and it will pass by the fuse before it can break and it'll still blow your unit, and that sucks. So sometimes the fuse can't even protect it, but most major appliances in your house have something to limit the current that goes through it in case of the easiest example, lightning strikes a power line near your house. That electricity is going to flow into your stuff, and this fuse will protect it, or the breaker will go off, or anything like that. All right, so kind of a quick question for this. Let me log into it. How much current will flow through a wire if 30 coulombs, that's a lot of charge, Remember, 1 coulomb is a lot of charge. If 30 coulombs of charge flows through it in, I think it said 2 minutes. Yeah, there you go, 2 minutes. Fantastic. And look at that, didn't even have to join code. You don't need the join code. All right, so how much current flows through a wire if 30 coulombs of charge passes through it in 2 minutes? Is the answer A, 15 amps, B, 1.5 amps, C, 0.25 amps, or D, 0.4 amps? I'm going to make these decimals a little easier to see. I'll put a 0 in front. Doesn't change anything. Me putting those zeros changes nothing, just makes it easier to read. We'll go to 50 seconds on this. This is a quick math situation, though you do have to be careful. So that's my hint. It's not as obvious as it seems. It isn't, it isn't. All right, we'll go to a full minute. All right, and we'll close this out in 5, 4, 3, 2, 1, boom. So, what's given? We got our charge right here. We have our time right here. But when you write those things, so that one's fine, no problem. But when we write our time, we don't like minutes. You got to convert that to seconds. So remember, y'all, base units. The base unit for time is not minutes, it's seconds. So it's a little tricky there. So current was defined as how much charge and how much time. So 30 coulombs and 120 seconds. Seems like a silly thing, but yeah, seconds is our base unit. Good to be reminded of that. There we go. And again, some of us got caught off by that, but hey, people tend to remember things better if they make a mistake anyway. All right, so great, super simple there. So here's my analogy for you all. Imagine I had a table with a bunch of marbles on it. Doesn't really matter what they were. Let's just say they're marbles. What could I do to this table to make all of these marbles roll at the same time? Yeah, saw someone gesture to it. Tilt the table. Tilt the table. Look, if you just push one of these marbles, it's going to have to, pushing just one of them ain't going to do it for us. Sure, if I push that, then it'll hit the next one, then it'll hit the next one, then it'll hit the next one, then it'll hit the next one. That's slow. I want all of them to move at the same time. So how do I do that? Yeah, I tilt the table. I rotate the table. And if I've rotated the table, I've introduced a height difference. I've introduced a potential difference across the two sides so that it is a lower energy on the low end and a higher energy on the high end. Just like electrons, y'all. Just instead of height. So, instead of height, that was my example with gravity, which again we're very comfortable with. Instead of height, I have a wire with a bunch of electrons in it, all over the place. Every single piece of metal, every material, even if it's not a conductor, but conductors are special because they're free, every material has electrons in it. Conductors are special because they're free floating. So how do I get all those electrons moving? I make one side a high voltage, I make the other side a low voltage, like a height difference, and those electrons see that height difference, and they all go to the higher voltage. Remember, voltage is not energy. Voltage is not energy. This side has a lower energy. Why? This is a good kind of reminder for y'all. Remember, y'all, U equals QV. This side, I have a negative energy. This side, I have a zero energy. A negative number is lower than that. Why is it negative? Because electrons are negative. So again, that's just a quick recap reminder. But yeah, they will all start moving. So when you put a battery in a circuit, that battery is not it is adding some electrons, but more importantly, the electrons in the wire, at every part in the wire, all see that potential difference, and they all start moving almost instantaneously. It's not like they're one's pushing another pushing. No. They all just see that potential difference, and they all start moving. That's why when you hit the light switch, when you hit the light switch, these lights, when they're off, they don't see a potential difference. When you hit the light switch, you close the circuit, and now they see, high voltage here, low voltage here, electrons start flowing, they flow through the lights, and due to a variety of reasons, that makes the lights makes light. So, that's what a battery is doing, y'all. It's introducing a height difference. I'm doing air quotes because, again, it's not height, but that's the analogy that I want you all to run with. That's how you can think of voltage and understand it. So yeah, there you go. And there you go. There's that example where I said lower energy at the negative terminal, higher energy, or negative energy at the positive terminal, positive energy at the positive terminal, and then they flow around. So it's cool stuff. All right, so here's a nicer slide than the one I had before, but it says the same thing. The variable for current is capital I. I had to specify because it looks like an L. It's capital I. I don't know the history why it's capital I. There's a reason. Oh, no. I do remember. It is because the French guy that came up with it called it intensity intensity of something. And so the I came from that word intensity, but it was the French word for intensity, whatever that is. And yeah, it's literally just defined as how much charge moves per time. It is defined as the measure of positive charges, but it's not actually positive charges moving through a wire. All right. The next slide, do not need to know it, but it's a fun fact. So just don't forget. Drift velocity is if you actually mapped out the path these electrons take, it's not a straight line. Because they're literally traveling through a bunch of atoms. So they bounce off the atoms in all different directions, but the net result is that they eventually make it to one end. So, the electron was moving and grooving, hit an atom, bounced off it, hit another atom, bounced off it, but it's getting pulled to the right. Think of it like rolling down a hill with a bunch of boulders in the way. You'll bounce off those boulders, but you're still going down the hill. Now, what's interesting about this, it's not very fast. If you look at the velocity of these electrons here, this is 0.000735 meters per second. It's really slow. But remember, it's not that when you connect that battery, the electron has to make it all the way to the light bulb to turn on. No, all the electrons are moving at the same point, kind of like a river. Every electron is moving just like in a river. All the water molecules are moving. And so, it doesn't matter that they're slow. There's a lot of them. There's a heck of a lot of them in a wire. So even though they're not moving very quick, the result is you got a lot of them. But it's just kind of interesting to know that they, one, don't travel in a straight line, and two, they actually travel quite slowly. But you don't need to know that. All right, we already talked about resistivity, so just reminding you, resistivity based on the material, different materials are better conductors. Great. You already did that? Okay. Now, do I want to do Ohm's law? Reminder that resistance is that. Let me double, triple check. Ready, did that. All right. So we're going to skip all this and actually talk about Ohm's law. Ohm's law, V equals IR. This is the relationship. We've talked about voltage. I just taught you what current is. We've talked about resistance. This is the relationship between them. If I have, so V equals IR, super simple relationship. Given a voltage, given a resistance, I can calculate the current in the wire. So when I mention current, we are not literally measuring current by counting how many charges pass through per unit time. I don't even know how you would do that. That'd be a pain. You need really fancy equipment. But you can find how many charges are moving per second with this super easy equation. Super, super simple. V equals IR. So if I have a 12-volt battery hooked up to, now this is where I'm going to start introducing some new symbols. In circuits, this is what a resistor looks like. That's a horrendous looking one. But it's this kind of jagged little line. This one down here is obviously much nicer than mine. That's a better example of what it looks like. But it's just this jagged little thing. This is how we draw a resistor in a circuit. We're going to be drawing a lot of circuits after test 1. So this is just a little intro into that. But if I have a 12-volt battery in a closed circuit, it's very important that it's closed. Because if it is not closed, if there is a gap, say I have this, and I did not close that end of the resistor to the other end of the battery, you need a potential difference for the charges to flow. As far as this resistor is concerned, everywhere is 12 volts. So remember, when we talk about a 12-volt battery, one end is 12 volts, one end is 0. It doesn't see the 0. It doesn't see the bottom of the hill. If it doesn't see the bottom of the hill, they're not rolling. If you're on a flat surface and it's 12 volts everywhere, you're not going to roll anywhere. I mean, I guess you could force yourself to roll, but the second, even if I get really close, still doesn't see it. All a switch is doing, when you all have a switch, it's literally just disconnecting it. The second that switch closes, now it sees 12 volts. Now it sees 0 volts. Now it sees a higher and a lower energy. And so the electrons, the current will flow this way. The electrons will flow the other way. Remember, current's the opposite, the way they're actually going. Okay, so we got all that. Great. Current's going to flow. And say, man, I sure would love to calculate that current if I told you this resistance was 6 ohms. Super simple. V equals IR. 12, the change in voltage. So remember, whenever I say the word voltage, it's always change in voltage. Equals I times 6. Divide that 6 on over. I equals 2 amps. That's it. That's how we use Ohm's law. Super simple. If I give you voltage and I give you resistance, you can find current. If I give you current and give you resistance, you can find voltage. Given 2, you can find the third. Now, how can they measure this? They can literally just do an experiment where they change the voltage. So you can see here in this thing, they change the voltage and they measure the current. The slope of this line is the resistance. The slope of this line is the resistance. So that's going to come into play. Y'all will do, there's a problem set problem with that. The slope of a line of voltage versus current is resistance. Rise over run ends up getting you there. All right, so this is a little silly one. I'm going to open it and then just kind of talk you all through it. So I'll open it, I'll talk through it so you can pick the right answer. So I've got a variety of lines here. So shown below is a beautiful graph with a bunch of different lines on it. A does this kind of like tabling thing, it's kind of exponential decay. D is exponential decay. A kind of plateaus. We have C, that's kind of exponentially increasing. We have B, that's linear. Ohm's law, what it says, when it says, does it obey Ohm's law? It means it's linear. So you are choosing the line here. Ohm's law says there's a linear relationship. So if we just look at our equation, V equals IR. You can see here R is kind of like, if you imagine that, I guess a little funky here. Imagine like that I is, it should be X in that case, which kind of gets confusing. But the slope, if you take the current and you divide it by the volt, you get the slope of this line is the resistance. The slope of this line is the resistance. And you can see here, there's no squared, there's no over it, there's anything like that. So the answer here, again, I'm just going to straight up tell you what the answer is, so all of you get it right. The slope of this line is the resistance. The slope of this line is the resistance. So the answer to this one's B. But let me show you all the problem I think that should be in here. 95% confident there's, if not, then I need, there it is. Voltage versus current. So when you are solving this problem, and the problem set, and it says, what's the resistance here? I've got voltage, I've got current. Rise over run, y'all. If I go up 200 and I go over 200 divided by 2, ta-da! It's very simple. But the slope of that line, as current goes up, or as voltage goes up, the current goes up, and yeah. So that's how you all solve that one. I wanted to mention that to you. All right. Close that out. Great job. Most people got it right. There's always a few that just, I think, randomly pressing it just to get the points. Whatever, I don't care. All right. Ready kind of did one like this. See if y'all can do it. So remember, this is the battery. I didn't show you all this. This is the symbol for a battery. So, in a circuit, no one wants to be drawing this whole shebang every single time. So this is a battery. This is the positive end. This is the negative end. It's a 5-volt battery or a 5-volt power supply. It doesn't actually need to be a battery. It could be anything that makes 5 volts. For example, your all's little adapter things. These make. Let's see. What's mine make? So this thing outputs. Usually they're written on it. So you all have power blocks that plug into the wall. They convert it to DC. We'll talk about AC and DC stuff eventually. But for now, just know that they output a certain current. They output a certain voltage. You all can look at those, and now you know what they mean. When you see 5A, now you know what that means. When you see 12V, now you know what that means. So yeah, 5-volt battery or power supply. 5-volt power supply. Let's make it a bit more broad. Not everything's run by batteries. 15 ohm resistor. What's the current? Is it 2 amps? Is it 1/3 amp? Is it 3 amps? Is it 75 amps? Or is it 1/2 amps? We'll go to 120. 130. We'll just go 130. In 5, 4, 3, 2, 1. So this problem, fairly straightforward. V is 5. R is 15 ohms. We're solving current. So step 1, what's given? Step 2, what are we solving for? V equals IR. And again, I've already kind of done one like this. So step 1, step 2, step 3. 5 equals I times 15. So I equals 5 over 15 equals 1/3 amp. When you are doing the problem solving process, I write steps 1, 2, 3, 4 just to make it easier to track. Obviously, you don't have to write that when you're doing the problems, but you'll see me doing that. If you're concerned for time on the test, don't feel like you have to write 1, 2, 3, 4. Use your time wisely. Okay, so great. Ohm's law, done. It's that simple. V equals IR, easy peasy. Relationship between voltage, current, resistance. So next, we're going to talk about power, and that'll be basically the last thing we need to talk about. We'll see if we finish all of it today. If not, whatever tiny little bit extra we'll do next time. And then we're just going to be doing a whole bunch of practice problems, y'all. That's basically what I'll be reviewing for the test. Practicing those vectors, identifying what kind of things may trick you up, all that kind of jazz. All right, so electrical power is the amount of energy lost or gained by a device every second. The amount of energy, basically, use the word used, converted is maybe a better way to put it. Remember, you can't destroy or make energy, it's just changing forms. So whenever we talk about wattage, we're taking electrical power, energy stored in the electricity, and converting it to something useful. Light bulbs, it's light. A heater, heat. It can be used for all sorts of things. So the question is, how much electrical energy is getting converted to something else? That's power. The unit is watts, which is defined as joules per second, energy per second. Joules is energy. The variable for power is P. You should hopefully have, this should be hopefully ringing some bells because you've hopefully learned about power in Physics 1. But in our case, power is going to be equal to IV, PIV. On your formula sheet, you are only going to see it as PIV. You are only going to see it as P equals IV. But then you're like, but what about these other two that are written down? I squared R. Or V squared over R. It's kind of like when we did that energy, we did something like this before. Remember, y'all, V equals IR. We just defined that. So, if I take V equals IR and I replace that V with I times R, so P equals IV. Let's go ahead and replace that V with IR. I get I times IR equals I squared R. Ta-da! I derived the second version of it. If I want to get the third version, I'm going to instead replace the I. So V equals IR. Rearrange that. I equals V over R. Go ahead and plug that into my PIV. So that equals V over R times V. That's V squared over R. Ta-da! I derived all three versions. PIV is the one that's kind of given. PIV, the derivation for it, is right down here. Super simple. Power is defined as a change in energy per second. Potential energy is Q times V. the rate of change of Q over time was current. So if I kind of just fill this little gap right here, change in Q over change in time times V, change in Q over change in time is the definition of current. So the derivation is fairly simple. It's right down there. Again, you replace all those D's with triangles for you all. Calculus, they use the D's. For you all, they use the triangles. But you don't need to know the derivation. What you do need to know is P equals IV, P equals I squared R, P equals V squared over R. All the ways to calculate how much energy is being converted to something else. Remember, you cannot destroy energy. You cannot create energy. When you all use electricity at your house, you are not taking the electricity and destroying it. You are using it for a functional task. Either to move an object, or heat up something, or light up something. What's really cool about all of this, y'all, electricity is one of those things that we get so used to that you're kind of numb to how cool it is. Because it's just so, like, it's all over the place. I mean, you plug something in, you get it. One of the really interesting questions is, why is electricity even, like, why is it so useful? And again, your immediate answer is, like, I use it to charge things, and I do stuff like that. Okay, but, like, take that one step further. There's other ways that you can do what you're doing. There's other ways you can make heat at your house than electricity. I could burn a log. There's other ways that you could make light. Burning a log is another way. What's really cool about electricity, kind of what I've stumbled onto, I haven't heard anyone else, I'm sure other people, it's literally an easy way to transport energy, and also it's a really easy way to take energy, and you can convert it to a lot of different things really easily. So I like to think of electricity as like liquid energy. It's liquid energy that's super easy to convert it from one thing to another. You can take electricity and turn it into heat. The energy stored in electricity, convert it to heat. You can take the electricity and convert it to light. You can take the electricity and convert it into movement. And you can transport it super long distances super easily. Back in the day, if you wanted to make heat and light, you either had to have logs, you had to have oil, all of that had to be transported by someone. Electricity, you just got wires. And it just like travels through them, and you can transport that energy thousands of miles, no problem. So it's just kind of a cool thing. Why is electricity so useful? It's liquid energy that you can easily convert to other useful things. I don't know. It's a cool idea. It's a cool thing to think about. I think it's interesting. If you don't, that's okay. My feelings aren't hurt. All right. So, same exact setup here. 5-volt battery, 15 ohm resistor. But the question now is, what is the power lost in the resistor? And by lost, we mean converted to something else. This resistor takes this electricity and it uses it for something. This could be anything. This resistor could be a toaster. This resistor could be a light bulb. This resistor could be an electric motor. It doesn't matter what it is. What it matters is that it is using this energy for some functional task. How much of that energy is it using every second? What is the power consumption of that device? Whatever it may be. This could be your phone getting charged. Is it 5/3 W, 2/3 W, 1/3 W, 3W, 45W? All those W's are watts. You may have to do a little bit of fraction to decimal to fraction, or fraction to decimal, depending on which way you want to go. Ooh, look at all them. A variety of different answers. Fun. We'll go to 145 on this, so 20 more seconds. In 5, 4, 3, 2, 1. All right, so shock and awe, the way to solve this is write down our givens. We have V equals 5 volts. We have R equals 15 ohms. We are solving for the power. We say to ourselves, P equals IV. And we say, well, that's extra steps involved. And then we remember either the derivation or you wrote it down or something. Hey, that's a better one to use. I've got V, I've got R. Now, alternatively, let's just look if we use this PIV one. You say, I want P, I've got V, I don't have I. You can find I. You can do V equals IR and find the current and then plug it in, and that would work. But using this V squared over R, that's already done that work for you. That kind of is like solving for I in the equation. So you get 25 over 15, common multiple of 5. There you go. 5/3 watts. We've got a variety of answers here. Now, when you plug this in your calculator, if you use this equation, you probably plugged in 5 squared divided by 15. That's what I did. And you're like, which of those answers is the same number as this? Just start doing them. You could just do 5 divided by 3 in your calculator, 2 divided by 3 in your calculator, 1 divided by 3 in your calculator. Which one gets you 1.67? 5 divided by 3. So, either you could convert this. So you know what? Let's just write the answer that it comes out in your calculator. 1.67 watts. You can either convert that to a fraction and go through that work, or you can literally just, this one's 1.67, this one's 0.67, this one's 0.33. Just plug them in your calculator and see what they are. Anyway. But it is that top one. Eventually it will highlight it when I collect the highlighter. It's never going to happen. All right. Great, I already picked it. That's what matters most. So, let's do another one. This one. What is the power lost in a 10 ohm resistor which has 5 microamps running through it? Did I not fix this one? I didn't. Terrible job, me. Secret option, none of those. So I don't know how I didn't have the right answer considering I used this one last year. Silly me. But hey, you'll get the answer right. Wait, can you even select E on it? Just to be sure. Secret option B is now 2.5 e to the minus 10 watts. And now I'm double, triple checking all of my things that I plugged in. No idea how I messed that up. But hey, we all make mistakes, right? Alright, so hopefully you know what the right answer is. Again, the bummer is the people that are online get a screenshot of the one with not the right answer. It's very sad for them. But I'll leave it up for a few more seconds. So, let's just solve this through while it's up here. So what's given? We got R equals 10. We have the current equals 5 microamps. We maybe haven't seen micro in a little bit, but it's the minus 6. We are solving for the power. And then the one that we're going to choose is I squared R, because we have I, we have R. So pick the one that has those things. So 5 e to the minus 6 squared times 10. And yeah, that comes out to the one I added. 2.5 e to the minus 10 watts. Not very much. So in case it wasn't, there it is. No idea what the delay is online. They'll see the answer eventually. Maybe too late. I will give them 10 more seconds. Maybe that's short enough. I have no idea. All right. And dead. Oh, look at that. Either I have 84 people in here or it did go through. And all is well in the world. All right. Fantastic. Okay, so let's solve some problems with this. It is very important I do, especially this one. So I'm going to straight up tell you this one here. So we're going to solve a few problems. We may not get to this one today, but we'll get to this one at least by next class. So I'm not going to do this one right now. I'll do this one probably beginning class Thursday or something. This one is calculating how much it costs to run an electrical device. I will straight up tell you there's a question like this on the quiz. I will also straight up tell you there will not be a question like this on the test. Okay? So we're going to solve through it so you have an example of how to do it for the quiz. Because I think it is cool to know how to calculate how much your different electrical devices, how much they cost you to run each year. It sounds silly, but it's a very practical kind of thing as opposed to most of the stuff we kind of learn in this class. So it'd be cool to see how much like different devices cost to actually run and how you calculate that, what a kilowatt hour is, and all that jazz. But that'll probably end up being Thursday. So we'll do some more of the ones that you actually will end up doing. So find the current through a person and identify the likely effects on this person. If she touches a 120 volt AC source, we'll learn about AC and DC next time. For now, just it says 120 volts. That's what we care about. If she is standing on a rubber mat and offers a total resistance of 300 kilo ohms, or if she is standing barefoot on wet grass and has a resistance of only 4,500 ohms. So this is a cool problem because it basically says which case you're going to get electrocuted. It's the second case. But we'll learn why, which is nice to know. So, what's given? We have 120 volts. We have two different resistances, so I'll just put one as R1, one as R2, depending on which part of the problem we're solving. You know, we'll say RA and RB. RA for part A, RB for part B. 300 kilo ohms. Anytime you see a prefix, we're going to have to convert it. The only exception to that is kilograms. That's the only one that gets two letters. And RB is only 4,500 kilo or 4,500 ohms. Okay, and we are solving for the current that flows through the person. Spend about 20 seconds. See if you can figure out what equation it's going to be. It'll be a nice one. So the nice thing is this week, the equations I give you all are fairly simple. Now, the challenging problems are going to be the ones that use a bunch of them. So like, let's see, is this next one that does do that? I hope so. Yeah, good. That next one's going to be a good one. We're going to see each equation by itself is simple, but then we'll use multiple of them together. All right, so hopefully V equals IR was already on your mind. If not, hopefully now it is. All right, so we have V, and you know what? Normally I put in the numbers and rearrange it, but I'm going to go ahead and rearrange it early. I just divided the R to the other side. Now I don't have to do algebra later. All right, so I equals 120. So for part A, 120 divided by 300 E3. Part B, it's going to be 120 divided by 4,500. Those are going to give us two different currents. 120 divided by 300 E3 comes out to 0.0004 amps. And 120 divided by 4,500 comes out to 0.0267 amps. Okay. It may look like that second one isn't that big, but it really doesn't take much to stop a heart. In fact, I have no idea what that number is, but I know who does. Google does. So let's see what Google says. So how much current does it take to stop a heart? Stop a heart. And this is, you know, we're going to do the classic strat of just taking the first thing that pops up. We'll scroll through them and, you know, see if they agree with each other. So, not very much. You know, we're seeing here 100 milliamps. That's 0.1 amps. Here we're seeing 0.007 amps. Here we're seeing 30 milliamps. We're getting a lot of different answers. But they get in the ballpark of 0.1 to 0.01. This one's 0.02. So again, it's in that ballpark. I would have to spend one more time because obviously every single one that we just saw. But this is in the ballpark of enough to stop your heart. 0.02. If that goes through your heart. Only kills you if it goes, goes through your brain. It'll mess with your brain. If it touches your hand, this may be shocking to you. Oh, that's terrible. But that's not. But I had a student literally take a paper clip and stick it in the, like I've had a couple students do that. high school, Now, these were the squirreliest of high schoolers, these two students I had. One stuck a paperclip in it, shocked him good. His arm was hurting after that. Now, thankfully, I don't know what path it took, but the real key here is this flow of electricity isn't going to kill you. Does it pass through your heart? That's what matters. If it kind of passes, above that, or maybe down the thing. All I know is that his arm hurt. Afterward, Ting did. He was, he got spooked by that. I had another student, so one literally stuck a paperclip in it. Wild. I had another student that, so our electrical plugs are actually really dangerous. The way they're designed, I am more scared, so I have a 2-year-old daughter. I'm more scared for my daughter being around something that's plugged in than something that's not plugged in. Because you can pull out a plug a little bit, and there's 2 prongs there, and if they stick their finger between those 2 prongs, yeah, one's positive, one's negative. So I had a student take a penny and put it between those 2. Not only did it flow through the penny and literally melt the penny, it also shocked their arm. And they also got really scared, and I called him an idiot. But it was just terrible. Again, these are my squirreliest of students. These were, yeah. So that is not the average high schooler by any means. 2 out of my 400, 500, 600. But yeah, this .004, that's fine. So rubber boots and stuff like that will actually protect you. Now, another fun fact here, remember, voltage, it's not the voltage, it's the change in voltage that matters. So another really interesting example of this is if a power line is down and it's touching the grass. So where that power line is, there's going to be a voltage, and that voltage is going to decrease the farther away you get from it. It's going to actually change over distance, because where it's touching is really high voltage, and then it will kind of decrease. So what's really dangerous near a power line is taking a big step, because you're introducing a high voltage and a low voltage, and it can flow through your body potentially instead of the ground. So if there's a down power line, you kind of do like the same shuffle you would do with like a Stingray. So that way you're not taking many steps. That way you're not making the distance between your legs very far. You're going to increase the likelihood a higher voltage is going to result in a higher current. Now, your body is very resistive. Your skin is not a good conductor. What is a great conductor is blood. Blood is literally a bunch of ions floating in liquid, and those ions, free charges, all that jazz. So yeah, if you touch something, you're not, so in the case of my, it still flows through you, but if it actually somehow, I don't know why you would do this, somehow broke your skin and touched the blood of it, and then, had another part, yeah, that blood would be a very conductive pathway. And when people get struck by lightning, they actually get these scars where the lightning flowed through them and actually burst the blood vessels, and they look like lightning. It's literally just their blood vessels have broken, and they call them Lichtenberg figures in wood. I don't know what they call those scars in people, but yeah, you can look them up if you want. Lightning will, you won't die. I mean, there's actually a low chance of dying when getting struck by lightning. All the fun facts. But yeah, there you go, y'all. So we'll do these last 2 problems, and this is it. So, on Thursday, I will straight up tell you all, there's not going to be any clicker questions. Thursday, Tuesday is just going to be me solving problems. I'll actually try to send out a survey sometime tomorrow asking what kind of problems would you like for me to work on. I have a sense of a few of them, but I'll get from you all what you'd like me to do during class. It'll be very much, hey, if you have questions you want me to work on, that's what I'm here for. We got the time, we'll use it. If you would prefer to study at home, you do you. But I will be here available and solving things, giving recommendations, and live streaming it as always for all the goodness. All right, y'all, have a great rest of your day. Good luck with things.